participants, good evening. I believe I'm audible to you all. Let me start sharing my screen. My screen is visible, right?
Yes, Shilpa.
All right, thanks, Mehul. So participants, I'm Shilpa from electrical team. Mehul has given a brief introduction about me. So one input from my end, what I'm expecting you from you is complete participation. Even if you cannot have a audible interactive session with me, I'm just expecting you to put down your piece of input and also the answers in the chat box. Please make use of it, because this would be great if we are taking it as an interactive session rather than kind of one speak or monotonous session. So let's start talking about the scope of power electronics in electrical vehicle. So it is a rather very interesting topic to begin with, because today we are going to understand the extent in which the power electronics technology have influenced the automotive sector or automotive industry. So we are going to check like in what length and breadth the power electronic technology has contributed for the neck-breaking phase of or rapid growth of electrical vehicle technology. So the demand of electrical energy, it always keeps growing, right? Particularly in electrical forms, it is ever increasing in order to improve the standard of living. By saying improving the standard of living, I meant that let's look at the devices which we are currently using now, right? So we have tab, we have laptops, we have LED lamps, and we have light controlled devices, we have sound controlled devices, right? So every year we are coming up with a lot of advancement in electronics field, and that is also rapidly growing. And that has grown into a phase where now we are looking into the automotive industry, and we are trying to come up with a wide range of advancement for e-mobility or electrification of automotive sector. So power electronics, what happens is that it already has found an important role when it comes to the portable devices and the domestic appliances which we are using. Now it is stepping foot into the wider aspect, that is into the automotive industry. So you might be thinking like, why we are talking about power electronics? What is the difference between power electronics and the normal or linear electronics, right? So that is a great question if you have thought about it. See, power electronics is a branch of electronics, but the golden rule, or let's say the golden mantra of power electronics technology is 2C, C and C, which is control and conversion of electric power. Whenever you listen to the word power electronics, or whenever you come across the word power electronics, just remember this two C's, control and conversion of electric power. That is what the power electronic devices and power electronic technology is looking into. So then you will be thinking like whether conversion is not happening in linear electronics. No, it is not happening. Then what about the operating voltage or power of these linear devices? Is it not competing with power electronics? Then what does it like completely focused into power electronics technology? So power electronics mainly helps in the efficient use of electrical energy. So linear electronics or normal electronics, definitely they are making use of electrical energy, but this guy or the PE sector is making use of the electricity in a very efficient form, that the efficiency of every device is been significantly increased. So the device efficiency, which we are talking about here, is between 92% to 98%, which is not applicable to normal electronic devices. So how is it making this efficiency possible? By reducing the losses and also by reducing the power consumption. If you look at the lighting devices like LED, light emitting diode technology, and the fluorescent lamp, I believe you know about both the lights, right? So why we have shifted from a fluorescent lamp to LED lighting? It because of the reason that it uses less power, right? And your current bill can go down. So that exactly is power electronics. That is a power electronics I'm talking about, right? So now think about in this way that this technology can actually revolutionize in every sector by controlling the power and energy. right? And now it has stepped into the e-mobility, which is the major technology everybody, or booming technology everybody is talking about, right? So this guy, like power electronics, can contribute to certain parts or systems of EV that can make an EV more usable, or let's say more efficient. So that is what we are going to see in a wider aspect today, like where we can use that and what is the influence actually caused by power electronics technology inside an electrical vehicle. So that is what we are going to see today. So let's just look at the agenda in a nutshell. So for understanding the scope of power electronics, you should be knowing two things: the basics of power electronics, or you should be having some idea about power electronics. That's what we talked about now for 1 to 2 minutes. And you should also have some idea about how does an EV work, or what is an electric vehicle, right? So everybody will be having a definition in mind that electrical vehicle doesn't have an IC engine. That's all. So that will be the very easiest definition you can give, right? So that's not a technical way of defining electrical vehicle. So there are lot other latitude in which you can define an electrical vehicle. So always as an engineer, when you see a system or electric vehicle or a vehicle, in the eyes of an engineer, is a design engineer, things are pretty different, right? Than seeing a vehicle as a user or driver. So let's see, like, what are the components, especially electrical components inside the vehicle. Then what are the types of power converters we make use inside electrical vehicle, and how is it being designed? Like, let's just peep into the hardware aspect of it a little bit. And we also will try to come up with a very simple Simulink model because of the time constraint. As you know, the power electronics concept and power electronic circuits are a little complex. In terms of design and also the controlling aspect, you have to create the whole closed loop control and all. So due to the limitation of time we have for this workshop, I just have taken out 3 simple models which we can develop using Simulink. So what we will be concentrating more is like how you can interpret the data, how you can interpret the design of that converter, and how you can read the results. Like as a power electronics engineer or a design engineer, how will you able to read the results? That's what we'll be focusing on while you are developing the circuit. So this is what we are going to see today, next 60 to 90 minutes. Okay, so now let's start with a small analysis. So look around you and tell me like how many power electronic devices you can identify around you. So you can put down your answers in your chat box. Yes, so I could, I have only one answer, that is UPS, correct? Uninterrupted power supply. Then what else? Microwave oven, okay. TV, okay. Inverter, great. Anything electronics. Anything electronics, I'll just go with only 70%. Modern, okay, it would be great if you are just completing it. Inverter, stabilizer, inverter of a FCBC, PWM. PWM is not a device, right? So I'm talking about, can you identify a device which work on power electronics? Washing machine, correct. So I think you mobile chargers, correct. Infotainment system, okay. Right. So I hope many of you can identify the power electronics devices around you, right? So all of them ECU. Okay. Electronic control unit. Can you be more specific, like which ECU? BLDC fan. Okay. Right. So DC-DC converter. See, I'm asking about the power electronic devices which you see around you, right? So can you be more specific where you are actually mapping to DC-DC converter? Laptop, speakers. All right. So where there is a conversion happening, or I can say that the power conversion is usually happening with any of these objectives. Like if you need a rated output current, if you need a rated output voltage, or you need a better performance from the system, definitely you have to work with a power electronic device. So one simple example, what I can figure out is a light dimmer, so and a fan regulator, right? So fan regulator, how does it work? The motor actually runs and depends upon the speed of the motor. You say that, fan speed also change, right? So how you are controlling the speed of the motor, or how you are controlling the fan speed? By using a regulator, right? So nowadays we are using a power electronic device, which is a regulator, and light dimmer, where you dim the light from one intensity luminous to other. That is also an example for power electronic device, right? A laptop, or let's say mobile chargers. Correct. All these actually are examples of power electronic devices around you. Super. So I'm super happy that you guys are, you participants are able to identify those power electronic devices. And what does a power electronic system do? As I said that it's just control and conversion. So either there should be a conversion happening AC to DC or DC to DC, or there should be a controlling happening, right? The value of the input power and the output power has to be controlled. And this is a black box where you make use of the semiconductor devices to implement that function, right? So whenever you talk about power electronics, semiconductor device or semiconductor technology comes along with it. It is aligned with the power electronic system. Without semiconductor technology, then we cannot actually fulfill what we say as power electronic device, because it is that switch or power electronic switch that is making the power conversion happening. So it is the major contributor, or I could say that that is a backbone of a power electronic device, right? The semiconductor devices which we are using, right? So let's move on to the next slide. As you know, the semiconductor devices which we are using, they are of different categories, starting from BJT, bipolar junction transistor, then we have triarc, GTO, gate turn-off transistor, the thyristors, then we have power diodes, IGBTs, MOSFET, right? So wherever you are using a power electronic device, either any of these switches will be used for it. And looking at the diagram, you can see what is the power capacity of this switches and what is the operation frequency for that. The reason why we are using this power switches is because of its operation frequency and power capability, right? So normal switches, it is not capable of withstanding that much high dielectric strength, electric field. It will immediately like break. So here the power semiconductor devices or semi switches, it has high current carrying capability and power handling capacity. And that is why we are using it everywhere. As you have mentioned, like we are using it in refrigerator, air conditioning, washing machine, right? The VCR, then the welding machine, motor control, UPS, everything, even to wider application like electric car and electric train, and automotive sectors also, they have find their way. So we are going to concentrate in this area where we will be looking into the automotive sector majorly. Now, if you look at the automotive sector, let's talk about the vehicle, right? So vehicle is not a single system. So if you're a user, if you're a customer, then you feel that, okay, I'm going to buy a vehicle, or I'm the owner of this vehicle. But in the eyes of a design engineer or in the eyes of an engineer, it's a very complex system. You could see that there are a lot of parts or systems associated with it, subsystems and components associated with it, right? So it is not easy to dismantle a vehicle and put it back together in hours or in days, right? It is a hard work of a lot of people together and a lot of different departments together that comes as a car model or car manufacturer, like a brand, right? So it is not an easy job to just understand the entire function within a short duration of time, or to make these systems within a short duration of time. In that way, we call that vehicle as a system of systems, meaning that system of systems actually refer to multiple independent system that works for a definite task or for one purpose. So when you talk about vehicle, it is a collection of multiple components. It is a collection of multiple system. Everything is independent, right? So the suspension system work independently, the battery system work independently, then the motor system work independently, but they all are integrated together to perform one task, which can be the propulsion of the vehicle, right? So in that concept, we call this as a system of systems. It more kind of independent systems working together to make one thing possible. So some of these parts they are employed technologies like ADAS connectivity and everything. So they will be more closely working with each other with the help of the ECUs. Then if you look at the component level, this is what you can see inside, right? So battery, if you look at the battery, then battery modules will be there, battery cells will be there. Then the powertrain will be having an inverter, an electrical machine, the charging system. So everything work independently, system level and also in component level. Right. So the propulsion system, energy storage system, the accessories, everything has to work together to make it possible. In that way, we call that as system of systems. Now, let's look at the aspect of what are the electrical systems that is inside an electrical vehicle or electrical EV component, right? So it starts with battery and charger, because whenever you talk about electric vehicle, even the fifth standard kid or in very layman concept, people say that electrical vehicle has a battery. It doesn't have an engine, right? Definitely. So that is an electrical system. So battery and charger together contribute to one electrical system. Then we have powertrain, which consists of inverter and motor setup, which we call as e-drive system, electrical drive system. Then we'll have all these auxiliary system or accessories, which is included as a function of vehicle, which is like headlamp, wiper, dimmer, right? All these accessories, AC unit, infotainment system, everything will come under accessories or auxiliary systems. So these are the major electrical systems that is included. And the power electronic technology or power electronics is everywhere in this. So you see 3 blocks there, everywhere the power electronics is influenced, or it has a footprint on its own, right? So let's see let's see like system by system, like how or what are the types of converters we have inside this electrical vehicle. So power electronics is a wide topic. It's like we have to plunge into this technology to know more about it. It's like you dig deeper and deeper, you get interested more, you find out more levels of converter, more topologies of converter. It's completely an interesting game when you go to power electronics. So look at it, the classification. The power electronic converters, majorly, they are divided into 3 types. One is DC-DC converter. Usually we call it as chopper. Then we have DC to AC converter, call it as inverter. Then we have AC to DC converter, we call that as rectifier. And AC to AC conversion, we call it as cycloconverters. So this guy, AC to AC, we are not considering for electrical vehicle, but rest of the guys, like 3 people, DC to DC converter, DC to AC, and AC to DC. All 3 are part of an electrical vehicle system. So look at it, the yellow highlighted blocks or yellow highlighted converter topologies, they are all used for high voltage and power applications. So definitely these type or topologies will be applicable for electrical vehicle, because there we are working with a traction battery, which has a range from around 300 volt to 900 volt, right? So definitely we need high power application converters over there. And the blue shaded or blue highlighted, they are used for low power application and all. So majorly the DC-DC converter we use are bidirectional converter, and the DC to AC inverter type we use VSI, voltage source inverters, and with multi-level inverters. And rectifiers will be using like single phase and 3-phase, right? So all these type of topologies can be implemented for the automotive sector. It depends upon the requirement of the power level, right? So this is the overview, or I can say that the bird view tree of or classification of how many types of topologies are available. Now let's focus more into the part where there is scope of power electronics, right? So as you can see, we have a traction battery here. There is a charging port. Then there are onboard charger setup. Onboard charger, we call it as OBC, onboard battery charger. Then we have auxiliary battery. We have thermal system, DC-DC converter, then the e-drive system, which consists of controller and inverter. And we also have traction motor. So these are the systems which you can see inside electrical vehicle. Now, where you can see these power converters, you can see in the form of a traction battery, where the power conversion is happening. It is an inverter, right? So what does it do? It just inverts the DC to AC. So this is basically a DC to AC converter. DC to DC converters are also seen, and you can see onboard charger, which are OBCs, onboard battery chargers, which has the topology or conversion of AC to DC, or we call it as rectifiers, right? So these are the three major topologies which we find inside electrical vehicle, and the design aspects will definitely depend on the power requirement level, like what type of traction battery you are using, what is the specification of the traction battery. That actually determines what should be the power output and design aspects of each power converter devices. Now, let's talk about a drivetrain and powertrain inside electrical vehicle a little bit, because it's essential to understand rather than these components, like how does the power is being generated and taken to the wheels of electric vehicle. So drivetrain is a set of components that will help the vehicle to move. So it is very clear from the definition itself, right? So train, let's just think about a normal train which has a lot of bogies connected together. So what does it do? It just move forward in one direction, right? And it has set of different bogies. Similarly, drivetrain is something that consists of a set of components that will help the vehicle to move, or it drives the vehicle, it helps in the propulsion of the vehicle. And what does it do? It helps in the distribution of power through these components so that the power is reached to the wheels and the vehicle is moving in the desired speed. That is the major role of drivetrain. Now, what about powertrain? Powertrain is something, as from the word itself, you can definitely understand that this is something which generates power, right? So we have a battery and we have an electric drive system that will be generating the power. So energy source plus the energy converter, you combinedly call it as a powertrain, right? So basically it supplies the power to meet the demand of the vehicle. While you are accelerating and decelerating, there should be enough power produced or provided to the motor input, and that has been done by the help of this powertrain, right? So this is about powertrain and drivetrain. Now, why we have learned about powertrain? Because our inverter and the e-drive system, the inverter plus motor combination, so these things are a part of powertrain, right? So I could say that the power generated from the battery is being distributed to the wheels with the help of, or generated from the powertrain, the drivetrain will be distributing it. And who plays a major role for the control and conversion of this power? It is the power electronics, right? Because just remember the mantra, it's like C and C. So whatever power is generated or power is captured from the battery, you cannot directly connect a motor to the battery, right? So sometimes as a kid, you might have experimented connecting a battery directly to a motor. In that case, a motor just spins in one direction and in one speed, right? So that is not possible when you are a car maker or when you are driving a car. Just imagine you are driving a car in only one speed. You cannot turn the speed, or you cannot decrease the speed. You cannot increase the speed. You cannot go for braking. Either you have to stop the vehicle or just run the vehicle in, let's say, 40 kilometer per hour or 50 kilometer per hour. That doesn't work that way, right? The car doesn't work that way. So that is the reason we have a power modulator that is sitting in between the battery and the electric motor, and that will actually helps in the control of the power. So whatever power is required, how much power is required at that moment for the dynamic action of the motor, only that much will be delivered to the motor. So who is doing that? It's a power converter device, right? So a power modulator that is doing. In that way, the power electronics actually plays an important role, or I could say that it is a brain of a powertrain system. Now, there are a lot of as I have said, the semiconductor switches are aligned or involved in this power electronics technology. And there is vast advancement in the field. So currently we are using MOSFET, IGBTs and all, and now we are looking forward, or we are shifting our focus into a technology called WBG, which is wide band gap devices, right? So we are trying to come up with, instead of just silicon, like now the semiconductor devices which we are using, they are made up of silicon. Now we are looking more into silicon carbide and gallium nitride type of material, which can actually have more power handling capacity. That devices you call it as WBG or wide band gap devices, right? So advanced semiconductor switches are there, and ferromagnetic material, right? So can anyone tell me like where can you find ferromagnetic material inside electrical vehicle? So you can put down your answer. So the question is like, where can you find ferromagnetic material? Correct. So Abhinav, Asif, everybody has given the correct answer. Magnets, correct. So where you can see the magnets inside the motor. So traction is something which defines the movement of a machine. So the machine we are talking about here is a vehicle, and traction means the movement of the vehicle. So traction battery means the battery which helps in the propulsion of the vehicle. I hope I have answered your question, Abhishek. Yes, correct. So motor, correct. And can anyone tell me like what type of motors are we using now? Yes, BLDC motor, then DC motor, okay. Induction motor, correct. Hub motor, okay, wow. So I'm happy that you know about hub motor. Brushless, okay. Brushless is BLDC again. Is BLDC a DC motor or an AC motor? AC, correct. Even if we say that it is brushless DC motor, it's not DC. Actually, it is a three-phase motor, right? So we are actually giving AC supply, and it works on AC. So correct, AC. Right. So we have induction motor, we have PMSM motor. Hope you might have heard this name, permanent magnet synchronous motor. And we also have PLDC motor currently used. So inside all these motor, you can see the ferromagnetic material, which is magnet, right? Now, the research is going on to find more heat resistivity and more advancement in this ferromagnetic material. So recently, Toyota, right? So Toyota, they are into the research. So hybrid electrical and electrical vehicle, Toyota have a lot of research, research happening in their sector. So they are proposing a new material which can be used for this electrical vehicle with higher end quality of a ferromagnetic material. So usually the ferromagnetic material we use is called it is a rare earth metal, and it starts with N. It's neodymium. Correct. So it's neodymium material has been used. So this material is actually heat resistant, right? So that's what like Toyota is researching on too. So these materials are also, a part of the entire powertrain because it is a part of motor. So it calculates around like 2 to 5 kg of total weight. So you can also see these materials in your entertainment system, let's say in speakers, radio, right? And in some sensors, then braking. So in few other parts also you can see this ferromagnetic material, right? So there are technologies research going on in that way as well. And safety, reliability, efficiency, so everything is a concern when you talk about powertrain and the converters, right? And the interfacing, like how easy to ride the vehicle. So that is also a major challenge, or the major point which you have to consider while you are a customer, also while you are a manufacturer, right? So this is one other picture where you can see the layout more clearly. So this is a plug-in type of vehicle where you have this microgrid, let's say charging point, charge point here. You can charge it. There is an onboard charger somewhere here, right? So that is called OBC. Then you can have an inverter. Then there is a thermal system, obviously, with every system, because cooling is a part, major part, right? And then you have a traction motor, right? So traction motor is nothing but the electrical motor we are using. Then you have auxiliary battery, then DC-DC converter, battery cell modules, and power electronics controller. So this is basically a layout, or it gives you a very transparent picture of what are the systems that you can see inside electrical vehicle. Now, if you look at the picture, you have battery, right? So the battery is actually placed on the chassis for many reasons. So you have a traction battery, right? And you have a auxiliary battery, and you have a DC-DC converter and an inverter. Then onboard charger, right? So for what purpose are we using this DC-DC converter? Because inverter you are using for connecting it into the traction motor. When you are using an AC motor, then DC to AC should be there. So DC is like the power from the battery has to be converted to AC for connecting to a traction motor. That is correct. And AC to DC conversion happens when onboard charging, because the charging point which you have here is AC, right? You'll be just plugging into a domestic, a normal grid supply. This will be AC, and for charging the battery, you'll be needing definitely to AC to DC converter, which is a rectifier. So that actually being taken care by an onboard charger. Now, where you can see this DC-DC converter, what is the use of DC-DC converter? Okay, variable voltage. Yes, ferromagnetic material used in tapes and hard disk. Yes, definitely the cost of the electrical vehicle can be high if we are going into more advancement of ferromagnetic material. So cost is definitely a major challenge. To produce less power, low voltage, operate to all auxiliary electrical system, light, as if, correct? HV, correct? Pranjal. I believe I'm pronouncing it correctly. HV conversion LV4, correct? Regulate output voltage of a battery, 72 to 12 volt, reduce voltage, music players. Okay, so I think major of you talking about the same point in different perspective. So DC-DC converters are majorly used for powering up your auxiliary system. As I have mentioned, you have a battery system, you also have auxiliary systems like headlight, dimmer, the wiper, your music system, or let's say the infotainment system, your AC, right? So all these electrical system doesn't need high power, right? Or high voltage. So these are all 12 voltage systems. Like it works in very low voltage application. So you need not take that power or that energy directly from the traction motor, because that can affect the entire, charge discharge cycles, and there can be affecting, it can be affected to the state of health and charge of the battery. So let's not touch the traction battery. Traction battery will be only focusing on providing the energy that is required to the motor. So let's just leave the traction battery to do its major function of propulsion of the vehicle. Let's not disturb it for your other accessories. For that purpose, we have an auxiliary battery which will be powering up this smaller electrical system. I mean, low voltage electrical systems, like whatever you have mentioned, your AC infotainment system and all. For that purpose, we need an auxiliary battery, right? So for that, we need the auxiliary battery will be like 48 volt or something. And again, the electrical systems need not necessarily be powered up with 48 volt. You have to buck it down or step it down to 12 volt. Right. So for that conversion, you need a DC-DC converter. So that is exactly correct, as somebody has mentioned, HV to LV, right? High voltage system to low voltage system purpose, you use DC-DC converter, or in other words, in layman concept, in order to power up your auxiliary systems, you need a DC-DC converter. So that is a clear picture, right? So again, we are not leaving with that picture. We are again looking at the picture batch wise. So you have a 12 volt battery. So it is going into, let's say this is the auxiliary system which we are talking about, or accessories which we are talking about, that is powered from a auxiliary battery. So you have power steering, air conditioning, water pump, everything from a 12 volt battery setup. Then the power controller unit, or PCU, it has a major function. So this contributes to the e-drive system or electric drive system, or this contributes to the powertrain part where you have inverter, DC-DC converters and all. Right? And then you have a motor and transmission system. So this is like DC to AC conversion happening. So this is the overall picture of power electronics influencing the entire electrical vehicle. So we already have talked about DC-DC converter. What does it do? It just converts the high voltage to a low voltage, and it will be powering up, your dashboard, multifunction display, and other accessories. Am I audible?
Yes,
Right.
Shilpa.
Okay. So did I miss because I just saw I was muted?
No,
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 right.
no. We are able to hear you clearly.
Okay, right. So with that, I would like to just take up 20 minutes for a small Simulink model, a very simple Simulink model, which we'll be creating just to understand, how things will be working, how you can design it, and how you can interpret the data or how you can read the results, right? So I'm requesting the participants, please be ready with your Simulink. Let me also open. So the problem statement which let me just show you the question which we are going to take up. So we talked about power electronics around us, right? So, and somebody has mentioned a laptop. So that was a real good, example, right? So power electronics around you, laptop charger, mobile charger, that is a real good example which you can work as a graduate, engineering graduate or a fresher. You can work on this topic. Actually, you can build that in Simulink. You can try to come up with that entire Simulink model. And even you can, if you have a laptop, old laptop or old laptop charger, you can actually open it and see like how many components are there, right? So in that way you can have a wider aspect of software design as well as hardware. So that's how you have to link everything together as a design engineer, right? So the question is like laptop charger, what is the type of converter we are using there and how many converters are we using there? Okay, I got AC to DC from Aradhana. That is correct. Good job. AC to DC. Okay. No, we are not using a boost converter. AC to DC and step down. Perfect. So Asif has given the perfect answer. AC to DC converter is used, which you call it as a rectifier, and definitely we have a step down converter, right? So what is the level of voltage? Can if you guys have logged in with your laptop, can you please check like what is the specification of your laptop, and can you put down in the chat? So I'm looking at my laptop adapter. So there is an adapter with you, right? So that is what the power electronic device which we are talking about. So my adapter, so I'm using Dell, and I am having 19 volt, 3.3 ampere and 65 watt. This is the specification of my laptop adapter. 20 volt, 1.5, super. Okay, thanks, Sriram. 12 volt. No, just look at your laptop adapter. 19.5, 65 watt, correct. Not 180, okay, 180, 90 watts. Right, so we are using different types of laptop and our specifications are different, right? Now let's understand like what is actually happening. Now you are plugging in your laptop charger to a domestic supply, which is 230 volt 50 hertz, which is AC, right? And you have a battery inside your laptop charger, which you just have read out the specifications. Mine is like 19 volt. Now, my current has been converted from 230 volt AC to 19 volt DC because I'm charging a battery. Battery uses a DC, right? So there are two types of conversion happening. One is like my AC is converted into DC. That means 230 volt AC is converted into equivalent 230 volt DC. Then that 230 volt DC is being stepped down to 19 volt, right? So that is what this adapter is doing. So he is a life saver, right? So he is like, he's helping us a lot. So there are two converters sitting inside. And if you just look at the adapter, if you just open it, you cannot see a bulky device sitting inside. It will be something like this, right? So there will be a PC board, BCB board, and certain microcontrollers or chips will be there. So it looks similar to it. That's why we talk about concising the or compactness of any power electronic device. Right. So that's what we are going to, develop. So what we are going to do is a buck converter, right? So AC to DC, we'll be looking at when we talk about OBC. Now we are going to develop a buck converter, which will be stepping down our input supply to 19 volt. So I have used my specification. So I believe it will be easy for everyone if we are using, the same specification. Now, please open your Simulink. And let's just quickly start with the Simulink part. So open your Simulink, and since we are going to design a buck converter, I believe that everybody are from electrical background, and you are at least familiar with how does a buck converter looks like and what are the components inside. If not, I'll tell you what are the block you have to be ready with. One is the diode. So this is from Simulink, not from Simscape. You should not take that blue color block. That is a physical model block, which is Simscape. We are talking about specialized power system block, diode. Then we have a MOSFET. So you can also take IGBT, but here I'm taking a switching frequency, which is around 20 kilohertz. So I have just taken MOSFET about 20 kilohertz. I'm using around 25 to 27. So you can take a MOSFET, then definitely a scope, then a constant block, because we have to define the duty cycle here, then a PWM generator, then a DC voltage source. Then I have taken a series RLC branch for making the inductor, resistor, and capacitor. So rest of the blocks we will take once it is necessary. So let's start modeling with these block diagrams. So I'll give you some time. Please be ready with the screen. And once you're ready with the screen, please put a thumbs up or just say ready in the chat box. I will be able to start with the modeling part. Okay, heat dissipation solution. So I'm not clear with the question. I believe that is it heat dissipation with the EV? Then we have a TMS system, which is called thermal management system. We'll be taking care of the entire, temperature management system of the battery. And for power electronics, we will have heat sinks associated with it, which can actually dissipate the heat. Okay, I only got one yes. So I'll wait for 2 more minutes. So once you are ready with the Simulink screen, Rishabh, it's okay. Like if you are not from an electrical background also, if you have the access to Simulink screen, please open your Simulink screen, go to library browser and just be ready with these block sets. So I'll keep my screen freezed for a few minutes so that you will be ready with all the blocks. Then we'll start modeling it. Right. So we'll just take around 10 to 15 minutes to go for the designing and modeling part. Then together we'll take around 20 minutes because we have still more, a little more theory part to get finished. And then we'll also go for other model. So by the time, please be ready with your calculator or please be ready with your notepad. We are going to start designing it, right? So we need to find out what is the value of inductor, what is the value of capacitor, resistor, and what is the switching frequency, then the duty cycle, right? So we are actually going to find out the design values or design parameters for the buck converter for our laptop charger. So please be ready with that. Yes, so this software is, yes, MATLAB Simulink. See, it is pulse, Suvin, it is pulse width modulation or PWM generator block. We can tell me the software we use for Simulink. So my version is 2022A. Okay, I'll repeat the components. So basically you need to get the components which is relevant for a buck converter, right? So buck converter it is a DC-DC converter, right? So it needs a DC voltage source for the input part. Then it will definitely need a switch, right? So I'm using a MOSFET. You can also use an IGBT, no problem. But here I am using a MOSFET. We will see like what happens with an IGBT also, right? And you need an inductor because it is an inductor current that is being controlled, right? So when you are switching off and switching on, it is the inductor current that actually defines the entire process. So you need an inductor. So for getting the inductor, I have used a series RLC branch. This is a Simulink model. So if you just click on it, branch type is RLC, and if you can go to L, this becomes an inductor. Similarly, I can do it for capacitor. I'm creating a capacitor from the series RLC branch. Don't go for RLC load, go for RLC branch. And I'm creating a resistor. So RLC, capacitor, R resistance, inductor, capacitor. These are the three components. Then definitely a diode, that should be a power diode. Then a MOSFET. Then the PWM generator to drive this switch. Then this is a constant because you have to define the duty cycle with the help of this constant block. This is the input source, voltage source. Right? These are the components. And please be ready with the notebook as well. So we'll just start designing it. We'll find the values, calculator and notebook, like 1 minute. Okay, let's start with our design. So for the easiness of calculation, I'm just considering the input voltage as 100 volt because, the supply, AC supply can start, the standard AC supply voltage can be anywhere between 100 and 230 or 240. So for the easiness of calculation, I'm just taking the minimum voltage as input, which is 100 volt. So the 100 volt, which we are talking about here, it is not the peak voltage. It is actually the RMS voltage. Now you need to convert this RMS voltage into peak voltage. So 100 into root 2. Let me write it over. So I'm just starting a whiteboard. I believe my whiteboard is visible. So let's start designing. So input I have taken, or let's say VI. My VI or V input is, I have considered 100. So this 100 is actually the VRMS value. So I need the VP value, I mean peak value. So what should I do? I should multiply this into root 2. So that is 100 into root 2 will be the value of my VP. So my input value is approximately like 141.4. Now when I'm doing this, I'll get this one. Right? So that is what should go into the input voltage source. So moving back. So just let me know if my Simulink screen is not visible. So my input voltage is 141.4.
Shilpa, we are able to see only the whiteboard.
Okay, right, fine.
Yeah.
Okay. So the value I have given it over here because that was the input voltage I have calculated, 141.4. Right. Now I should be calculating what is my duty cycle of the buck converter. Right. Anyone knows what is the formula for duty cycle of a buck converter? So buck converter duty cycle is defined as D. And how do you calculate it? It is a very simple equation, which is V out by V in, right? So V in we have already calculated, which is 141.4, and V out I am taking my laptop reference 19 volt. So you can also take mine for easiness of calculation. So 19 by 141.4, that will be your duty cycle ratio. So this should come around something around, let me also calculate, 19 divided by 141.4. This should come around 0.1347, right? Approximately 13.47%, or I could write it like 13.5%, right? So this is the duty cycle, meaning that my switch should be turned on for a duration of 13.5% during the entire cycle, right? So this value should go into my constant block. Here, where I should be giving, so I'm just taking the fractional part. I won't be checking the percentage. So this should be 3.135. Right? And I can directly connect it to here because this is the duty cycle. D I have defined. Okay. Then I can place my switch over here because from the connector, from the DC voltage source, the connection is going to my switch. Now I can give the pulse from here, pulse generated to the gate. So I believe you know about 3 legs of the MOSFET: drain, source, and gate. So gate is where you are triggering the, or you are giving the control voltage or control signal. And what is the duration of, or the pulse width of the D? It is like 0.35, right? So I have completed some part of it. Now I have to connect the other components as well. And also I have to design for my inductor. So diode, I'm not going to do anything here. So I'm simply like rotating the diode. So for rotating the diode, you can just simply press Ctrl R and you can rotate it. And I can connect my diode. I'm just placing it. So let my scope sit over here. I'm rotating my capacitor. My inductor, my capacitor, and my resistor. So resistor also I'm rotating. Positive terminal going up, and scope, let it sit here. Okay, I have connected my diode to my inductor. Then I'm dragging and connecting to my capacitor. Then I'm making the connection for my resistor. Similarly for the negative part or ground part as well. The low potential part, I'm just creating the path. Now source to, perfect. Now my buck converter connection is completed. The only thing is that I should be just having measurement block, or the measurement from my resistor or output voltage, my current through the inductor, right? So all those measurement I'll be keeping over here in the scope. Before that, I should also go with the design value of my inductor, capacitor, and resistor. So till now, I have only configured my DC voltage source, which was 100 VRMS. So I converted it into peak voltage. Now I should be taking 141.4. Then I just found out what is the conversion ratio of my switch, which was 13.5%, means that 0.135. I have connected that to a PWM generator. I'm not configuring anything over here other than the switching frequency. So switching frequency here is given as 5,000. Since I'm using a MOSFET, I can take values, near to 20 kilohertz or something. So for my easiness of calculation, I'm taking 27 kilohertz 25 kilohertz is also fine. So let me take 27 e raised to 3, right? It's just assumption. Now I have to consider this frequency for calculating my inductor, capacitor, and resistor value, right? So these are the values I have added. Right, so going back to the designing part, let's just design for rest of our parameters. So still now we have designed for duty cycle and we have stopped by then. Now next thing we have to calculate is what is the current through the inductor. So current through the inductor is IL. What is the formula for IL? It is basically like I0, like output current. So how can I calculate it? If I know the power, P divided by V0. I know the power of my laptop adapter, which is 60 watt, and V0 I'm expecting 19, right? So 60 by 19 will be your current through the inductor. So that is 3.15 ampere. I should also consider some ripple factor for the inductor. So I'm considering 1% of ripple factor, that is delta IL is equal to 0.1 into 3.515, right? That gives me 0.315 ampere. So I have calculated, till now I have calculated my duty cycle. Then I have calculated my inductor current. And I have assumed 1% ripple factor for inductor, and I have calculated the ripple inductor current as well. Now let me calculate the resistor R, load resistor. What is the value for resistor? R is equal to, it's fairly easy. It's like, V out square by P. P is the power. V out is 19. 19 square divided by the total power. Expected power will give me my resistor value. So 19 square by 60. That comes around 6 ohms. Correct, 6.1, 3.6, yeah. Great. So I believe you guys are able to follow me. Those who are following along with me, great. Good job. So I'm just going to, highlight the points, duty cycle here. Then this is the V input, right? So V input. V input, which we have configured as this one. Then IL, which is the current through the inductor, is this one. Still, we haven't figured out what is the inductor value. L value, inductance value, we haven't figured out. We just calculated what is the current going through the inductor. That's all. Then we calculated, we assumed an ripple value, which is this one, right, with the formula. Then we also found out the R value, which is this one. So you can also go back to your Simulink model and start configuring it. So we have configured only VI and we also have given duty cycle. Now go to your R resistance value and just give it 6 ohms. Don't give inductor value because this is not what we found as L. This is current through the inductor. So do not configure the inductor now. It is just a resistor value you can add into. So we are left to find out capacitor value and inductor value. So resistance in ohm, apply OK. Right, MOSFET I'm not touching this anywhere, like let everything be default. Switching frequency, I'm considering 27 kilowatt, even if like 25 kilowatt also you can consider. Right, so we are left with this two design. So let's go back. So let me write it with a different color for L. Now L is equal to, the formula for L is a little complex. So V out into 1 minus D divided by the switching frequency Fs into delta IL. That is equal to V out is 90, 1 minus 0.135 divided by Fs. I have taken 27 kilohertz, right? So 000 into IL is 0.315. So if you're solving this, you will get your inductor value. So first solve this one. Like what is 1 minus 0.135? That comes around, I think, 0.865, right? So 19 into 0.865 divided by 27,000 into 0.315. Ahsan, just for your understanding, so EV webinar doesn't mean that we will be able to teach you the entire design of an electrical vehicle. So this is related to power electronics and scope. So here we are trying to understand how does a DC-DC converter work, right? So for that, we have taken an example of laptop charger circuit for your understanding. Now, if you want to calculate for a DC-DC converter, let's say you can also take the input and output value of an auxiliary battery. That is our next activity. So we'll be just trying to understand how does a work, how does a buck converter work, how do you design it, right? So design is what we are focusing here. L value I got around 2 microhenry. Okay, 0.0019. Fine, 1.9 microhenry. Okay, so I got around 2 microhenry. That might be just no tuning difference of the values which we have taken. So let the e raised to -3 be there. 2 microhenry. And we are only left with the design of capacitor. So design of capacitor. Let me erase, or let me write it with a different ink. Here, C is equal to, I hope my screen is okay and you are able to see my screen, and writing C value or C out is equal to 1 minus D by 8 into L Fs square delta V0 by V. So here also the ripple voltage of the capacitor you can consider as 1%. So that will be like 0.1, right? So this value you can take it as 0.1. So 1 minus D is around 0.865. Then 8 into here it's Fs square. So divided by 8 into L value is 2 microhenry, that is 2 into minus 10 raised to -3. Then F is 27 kilohertz square, right, into 0.1. So the design equation of capacitor, it's written in green. So I'll repeat, 1 minus D by 8L Fs square into the ripple voltage under consideration. And once you solve this, first solve this equation, then divided by 0.865. So the capacitor value will be something around how much? 7.4 or 0.0050 741 farad. Right. So let's go back to our Simulink. And let's just add the value for our capacitor. So I'm using the entire value. I'm not giving any decimal point here. Sorry, I'm just writing as if I got the calculation just to avoid any mistakes. So there are 5 zeros, then 7416 farad. Okay. Now I should be measuring the voltage, right? So for that, I'm voltage and other few other aspects. So I'm using a multimeter. Right, I need more multimeters. Okay, so here let the simulation voltage be 1 just for the easiness. I'm trying to simulate it. Okay, there should be a power GUI block. It will throw an error because I haven't kept the power GUI correct. So let's take a power GUI block. Then let's run it again. Okay. Okay, no errors. So I'm just stopping it and let's just configure the multimeter. Okay, I haven't defined the measurement. So I wanted to understand the branch voltage. And then also I wanted to see my inductor current. Okay, that's it. And I'm opening my multimeter. Yes, so I'm using branch voltage. UB. Then I'm using the other multimeter for my inductor current. Okay, let me connect it to the scope. So this one will give me my voltage, total voltage. Ideally, that should be 19 volt. This one will give me like my current, inductor current, which we have calculated around 3.15 ampere. That should be coming into the simulation part. And I'm also like, connecting my diode and MOSFET to see like what is the current from my diode and MOSFET. So I'm connecting that as well. So what should I have? Since this is multi-dimensional, like I should have a bus to vector block because,
Hey,
multiple signals are
Shilpa,
coming. Yes, Mehul.
sorry to interrupt. How much time this will take for you to finish?
Another 5 more minutes.
Okay, and then another model is there, or that's it?
No, we will be continuing with some more content. Then if time
Okay.
permits, we'll just go for one more model.
Sure, sure, sure. Okay, thanks.
Yeah. So I'm taking a selector switch. and connecting it. Again, one more bus to vector for the diode. Then again, one more selector for diode. See why? Because we have multiple signals coming from diode and MOSFET, right? So we should be selecting like which signal we want to view in the scope. So basically, I am referring to the current, diode current and the MOSFET current I want to see in the scope result. So that is why I'm keeping a bus to vector, meaning that from multiple signals, it will help me to diverge it to only a single vector signal, and I can select like which signal I can use it for. That's the reason I'm using a selector here. This becomes a little clumsy. Let's just make it quick. So we'll take 5 more minutes to simulate it. And then let's just get back to the content. And, you can practice more. Yeah, thanks, Ganesh. Selector was not connected. Right. And let me go into the selector. Yes, so input port size, I just need 2. And okay, I don't need 1 and 3. I just need only 1. Okay, hope this will work. Yes. Similarly, change it to 1. Then I just need 2. Okay. Right. So I believe, the model is ready. Let me just make it a little more presentable. Like you can see there are a lot of lines and all. So by the time you can also just make sure that you have completed the design and connected all the models, all the components together. And please save it. Let me just save it. It'll sometimes my MATLAB crash if I'm just saving it. So for safer reason, I'm just stopping the screen share for a minute. So by the time you can also save your model and make it more presentable. You can annotate the model, like you can give the values like V in, then V out, right? You can calculate like what is a duty cycle. So you can write it over there, right? DC buck. And you also use a voltage measurement block for your, V output voltage. So since my model become a little clumsy, I'm just replacing it with a go to block from block. Let me share my screen. Right, so this is how my model now looks like. So what I did, I just saved it like buck converter, and I just gave a go to block and a from block so that I can just connect my scope a little bit more presentable. So rest of the things are same. right? So let me give one again and let me simulate it. So ideally I should be getting some 19 volt. Yes, I hope my screen is visible. My scope is visible, right? So here you can see it is coming 19. So V out is around 19 value, right? And rest of the things are also being good. So let me make it more presentable. I believe you guys know it. Okay, this is fine. No, you can change your layout over here. You can also make the visibility of your line more reluctant over here. Okay, let me apply it and see. Okay. Right, so axis color. So you can change things over here. So I have only changed the first one, display one. Now if I'm changing it again, each of my diagrams will be changing. My simulation results color will be changing. So you guys know about it. I'm just trying to do it again, just to see whether this can be more presentable. Instead of a black screen, just seeing like whether we can go for more colors. Yeah. Right. Okay. So auto scaling it. Let's say quickly figure out whether I got the results from a buck converter. Yeah, so I'm getting around 19 volt with some ripple factor because we have considered an output voltage ripple of 1%, right? So that has been reflected over here. Right. And if you look at the data, so this is IFET, right? So that is the current from the MOSFET, and it is around, let's say 3 point something. And if you see, it is like vice versa, right? So when the diode current is flowing, the MOSFET current is not there. And look at the inductor current, it is around 3.3, which we have already calculated. And if you look at the averaging, it will be like 3.15. Whatever we have calculated, 1.5 or 3.2, that will be coming over here. So whatever we have calculated, the design is actually reflecting in your simulations. Now, if you look at the inductor value or inductor current, you can see whenever the inductor is off or whenever inductor is not bypassing the current, the diode is actually the diode current is prominent, right? So whenever the switch is on, then the inductor current is rising. So that is what you can interpret from here. Fine. So I am happy that we got the results like almost in perfect way. So if you want to practice more, I think we still don't have much time for taking up again a practice. So I thought like we can at least cover 3 models, but I think that is not possible. So what you can do is like you can just have practice for the DC-DC converter, like the auxiliary converter, right? So these are the formulas which we have used for our designing. And this is how the complete model of a laptop charger actually looks like, because it will have an AC input side where the AC is converted into DC. Like if you just look at it 100 to the DC 100, then there will be a rectifier stage, right? Then there will be a buck converter stage. So we have worked on only this part, right? And it took a lot of time, right? And this will be the battery. So this is the battery charging setup of the laptop. So this is the entire model which you can work on if you want to practice or something, you can just work on it with the AC supply voltage, the rectifier stage, the buck converter, which we have developed now, and the charger setup. So this is just a battery. So this is how, like, if you want to practice an actual EV setup. So EV setups and power electronics are kind of complex, right? So you cannot do it within 5 minutes or 10 minutes. You need a lot of practice to do that. You need to understand a lot of detailing of design, right? So maybe we'll just have only a Simulink model practice in our upcoming sessions with some vehicle to grid technology or something. We will not touch upon any kind of content. We will directly go and start simulating it. Maybe we can plan like that for more understanding about the power electronic model in the EV. So here what I thought is, like, you just have to understand how to design it and how to look at the result, right? So how you are going to simulate it and understand it. And we have done it for a simple laptop charger. So next activity was actually auxiliary battery system, where you can convert 48 volt to 12 volt, right? So you know the design now. It is basically a buck converter. You know how to calculate each parameters, inductor, capacitor, duty cycle and all. So do it and try to build up the Simulink model from your end, right? Now, only part we are left with is, like, again, moving on with the content part. We have traction inverter and the charger setup inside electrical vehicle. Now, traction inverter, like where we are using it, we are connecting it into the electric motor, because an electrical vehicle doesn't have clutch or gear system. It is single transmission system in which the speed of the entire vehicle, speed of the electric vehicle has been controlled by the inverter. So for that also we need power electronic concept. So inverter make use of DC to AC conversion, right? So with an electric drivetrain, the inverter controls the electric motor. Motor controller is basically an inverter, right? And it also helps in the regenerative or electrical braking part, right? So this is a key component of the car. Similar to IC engine, we have an engine management system. So similarly, the inverter actually understands the entire driving behavior, regardless of whether the motor is synchronous, asynchronous, or BLDC, brushless DC. The inverter will always function in a similar way, that it is integrated with a PCB, and it will be trying to minimize the loss. It will be trying to minimize the thermal part. Then it will be enhancing the entire function of the motor, right? So that is the main part where inverter works. Now, basically, the inverter control is three-phase vectorial control. So for controlling the inverter, you need, again, power converter switches like MOSFET, IGBTs and all, and there will be multi-level inverters involved. You'll be having three-phase as well as single-phase inverter, and there should be multiple number of MOSFETs included. Like, you cannot work with a single MOSFET when we are using a DC to AC inverter. You should be working with 6 or more number of MOSFET, right? So we call the control as a vectorial inverter control, which is basically SVPWM. You might have heard it. Space vector modulation, space vector pulse width modulation technique is basically used for controlling the inverter. So it is a very complex circuit. Inverter is very complex, and the control of the inverter is also complex, right? So that is about inverter part. And then we have, the picture of inverter. How does it looks like? So this is a simple inverter. So while you say inverter, you might be imagining a bulky system. No, now everything has come to a very compact size and concise size, where it is chip level, right? So this is basically the picture of inverter. And these are the major application of electrical appliances in EV, right? So if you look at it, everything, almost everything, 99% of it, it's electrified. Starting from the entertainment system, you have mobile charger port inside vehicle, you have airbag deployment, you have control ECU, then you have monitoring systems like sensor monitoring systems, you have battery management system, right? Power steering, electronic throttle control, everything inside, outside of electrical vehicle, it's completely electrified. And there, everywhere, some part of it, the power electronics plays a major role. So the only part left is this part, right? So onboard charging setup. When you're plugging in your electrical vehicle, again, the grid which you are plugged into is a AC grid. Usually it is an AC grid. So here we are talking about AC to DC charging, level 1 and level 2 charging, which is AC to DC. Now your onboard charger is nothing but it is an AC-DC rectifier, similar to a laptop charger adapter, which you have mentioned. Like there are two converters, AC to DC and DC to DC. AC to DC is a rectifier which will be sitting inside as a battery charger, onboard charger setup, and that is connected to a DC-DC converter. Because again, whatever we have done now, we just try to control, we converted it here from AC to DC, then we controlled the voltage, right? So, and then fed into the battery for a laptop charger. Similarly, for electric vehicle also that will be happening. There will be an AC-DC setup and then DC-DC converter that is, providing the charge to the battery. So this is called an onboard charger or OBC. And there are offboard charger also. So offboard charger we are using mainly for level 3 charging, which is called DC fast charging method. So for AC charging method, we will be relying on an onboard charger. And for offboard charger, we will be looking forward for DC to DC charging, fast charging setup. And now we have one more technology, which is called vehicle to grid technology. It's not like you power up your vehicle, you charge your vehicle from the grid. So grid is something which is the electrical distribution system, right? Or, from where the source of electricity. So it is not like you are powering up the vehicle from the grid. You can also provide the battery power or the excess battery power to the grid also. That technology is called vehicle to grid technology. So the electricity now can flow in both direction, bidirectional. So for that purpose, the OBCs or onboard chargers, the topology which we are using is bidirectional converters, where the energy can be flown in both directions, from grid to battery and battery to grid, right? So bidirectional converters are majorly used as onboard chargers. Now, what is what happens here? Like it helps in the fluctuation. Like if there is a fluctuation, or you might be know about power factor correction, right? So that can be reduced by using a bidirectional converter, and it also helps the EV owner to sell some of his electrical energy to the grid and get some money. So monetization is also there, right? So similar to how the electrical distribution companies or microgrid is providing energy to the vehicle, you can also sell back the energy from your vehicle and you can get some exchange of money for each unit of power you sell, each unit of energy from the battery you are giving back to the grid, right? So that technology is called vehicle to grid technology, and it is a complex system. Like if you look at the power electronics part of it, you have a front end converter and a back end converter, you link it together and you try to implement the bidirectional conversion there, and that is how it's completely implemented. Right now, everything, like keeping aside everything, whatever power electronic system you have inside an electrical vehicle, it should go through certain process, right? So it starts from the specification, understanding the specification, understanding the requirement, and then coming up with the final product. So it's simply not like you will think about a value and you start modeling it. It's not like that. First, you understand what is a converter specification, then you create a design environment similar to what we have done now in Simulink, right? So there will be a simulation environment which you will be creating. Then you try to analyze it, like you try to analyze the results. How is it coming? It is coming in the right way. So there is a statistical method, you analyze it. Then you go for certain prototyping. Then you understand which environment you have to make this possible, and then you go for the final product. So that is how the entire design concept work, right? So there should be a standardization for everything. So you cannot just go and pick up any MOSFET, or you cannot just go and pick any diode for you. So it depends upon the design values you have. It depends upon the final output you are expecting, and depends upon each and every aspect of it. So fine tuning or the power electronic design is very sophisticated, because it even you change a single value, it can actually affect the output in a very drastic way or significant way. The result can actually vary. So the power electronic design has to be done in a very sophisticated way, that you are very thorough and very precise about the design, right? So once you understand the design, like once you understand the specification, okay, I need a traction battery of 400 volt. Now what should be in my OBC? So you should reverse calculate it and try to understand like each MOSFET, like what type of MOSFET I should be picking up, what type of diode I should be looking into, whether this MOSFET or IGBT can have that power capable capacity, power handling capacity, whether this can withstand the temperature. So everything you have to look into in a very deeper way, and you have to design your entire system. So understanding the specification, then the requirement, for what purpose you are using that, then you analyze what should be the output and input, then you understand the controller, the controlling method, like whatever we have done, the MOSFET, IGBT, how does the control of electrical current has to take place, electrical power has to take place. Then is there should be any sensors? Definitely, like you have to sense certain parameters, right? The system parameters are always like temperature, voltage, current, power. So you have to sense it. Now, where to fix it? So everything as a design engineer, you should be having something in mind. Then you go for validation. Once it is completed, go for validation testing. Then you should also understand what is a bill of material, BOM. How much does it cost for your MOSFET, the MOSFET which you are using, the power switch which you are using, the power diode which you are using. Then how much it costs for your inductor, what is the size of the inductor, how can you reduce the size of the inductor. Everything as a design engineer you should be very thorough, and then only you go for the testing, final product, for the prototype, then for the testing, and then you go for the final product and implementation. So every process you go through as a hardware engineer is very delicate and very fine tuned in a way that you do not mess up at the end of your output. So that is how the hardware design takes place. And this is how each module actually looks like. So as we have, drawn in Simulink, it doesn't look that much beautified. It is actually look like, PCB board, green color with lot of small components. All these black color, they are microchips and microcontrollers, the resistor, capacitor, these are input port, output port, right? So the entire structure of the component itself is different from a block diagram, from an electric schematic percentage to a hardware setup. Entire thing is different, right? So this is the power module. You can see these are IGBTs. There are 6 IGBTs together. It's like 3300 volt. This is the control card, where what we have done is an open loop. You definitely need a controller for stabilizing the output of the power converter. So this is how a control card looks like. There is a sensor card for understanding or sensing the voltage, current, temperature parameters, right? And the isolation card. Definitely there should be some safety features included, and if some component goes wrong or malfunctions, there should be the entire device should not be in danger. So there should be some isolation card, right? So in hardware perspective, the entire setup actually looks like this. It's not that much beautified like a Simulink model. Now, coming to the last part, what's the news, right? So what is actually happening in power electronics industry? Recently in electrical vehicle, we are now moving towards 800 volt battery systems. So currently almost all the battery design or the car makers are in and around 400 volt range for their traction battery. But now we are upgrading ourselves from 400 to 800 volt battery system. And how we are making it possible with the help of wide band gap semiconductor devices, which I have mentioned in the start of our webinar. So we will be using, instead of just silicon and germanium, we will be using gallium nitride and silicon carbide as the semiconductor materials. So it was proved that using these materials as the semiconductor devices will be having high power handling capacity, and it can withstand high dielectric strength, or let's say high electrical current through it. Right, in that way we can have a more range of power handling capacity for the entire power module, in which the battery range also can be increased, because currently the challenge is like your MOSFET or IGBTs have certain range. So after in which, like if you're passing a higher current through it, it can blow off, right? It can burn. So now with the help of the semiconductor device or semiconductor material used as a switch, it will withstand more current. So even if you are giving a wider range of current, it is possible to withstand it. So you can increase the possibility of power handling capacity totally. And that is the reason you can elevate, or you can go for a facelift for the entire battery architecture. So that is a new technology that is running in the research and development of power electronics, and there will be more advancement coming to our end when we have more infrastructure and when we come up with a lot of manufacturing companies as well. We will be definitely having more scope of power electronics, especially vehicle to grid technology is one such scope which we have, that a consumer, a driver, or a customer can actually get paid when if you have an electrical vehicle and if you are able to provide some charge from your battery to the grid. So grid is nothing but it's an electrical distribution system. It's basically like the source of electrical energy from which you are taking the electricity. That's all. If you have a charging infrastructure or a charging point, that is a grid. If you have a solar installed at your home, that is a grid. That you call it as a microgrid. So basically it refers to a source of electrical energy. That is called grid. Right. So that is the latest news in power electronics. And we couldn't do the activity for AC to DC converter because of our time constraint. But that's it from our end regarding just going through the periphery of the scope of power electronics, and there are a lot more details which we can discuss. So this is just a basic which we have looked into, because 2 hours of time is not enough to talk about power electronics and the details. So maybe in upcoming webinars or any other sessions, we will again meet for vehicle to grid technology and how to model actual EV power systems. We can just try with that if we have around 2 to 3 hours of time. Just omitting all the content, let's just jump directly into the Simulink model, and let's just come up with a good model for EV regarding power electronics, right? So I hope you got some idea regarding the scope of power electronics and some idea of what is happening in the industry and new trend, silicon carbide, gallium nitride, then traction inverter, grid. I hope you got some idea. You got some knowledge upskilling for the past 2 hours. I believe so. Yes, Mehul, that's it from my end. Thank you so much. If you have any questions, please put down in your chat box.